architecture, and that is a fundamental architecture which is used whenever you're learning embedded systems. So mostly anybody who's learning embedded systems as a course will encounter what we call 8051 architecture in their learning process. But when you go out there into the market, I mean, when you go out into the embedded market, you will see more than 80%. Okay, more than 80% of embedded systems will be designed mostly using what we call the ARM architecture. And apart from that, apart from the ARM architectures, you will also have, of course, some embedded systems which are designed using 8051 architecture, using PIC architecture, using what we call Renesas architecture, using Motorola architecture, and using AVR architecture. So there are lots of other architectures also out there in the what we call global market, other than the what we call 8051 architecture. But among these various different CPU architectures in the world of embedded systems, it is mostly dominated by the ARM architecture, and a little bit of role is also played by other CPU architectures other than ARM architecture. So what you are going to learn here is an overview. Okay. Voice is audible?
Sir, voice not at all audible, sir.
Not at all audible. Oh my God. Where is it going wrong right now? Let us see. But your voice is audible to me. Can I, is it audible now? Now audible? Everybody?
Yes, sir.
Okay. Right. So the ARM architecture happens to be one of the dominating architectures in the world of embedded systems, which is taking more than 80% of the embedded systems design. Okay. So what we are going to cover in the Vector Institute about the ARM architecture is, of course, usually whenever you learn about any CPU architecture, a bit of architectural features, and after architectural features, then we'll move on to what we call programming in terms of assembly and in terms of embedded C. Okay, so once we go complete this architectural overview and programming in terms of assembly and embedded C, then we can move on to what we call the application oriented, such as the interfacings and the protocols like that. So we can go on for that. So when we talk about the ARM architecture, actually the popularity of ARM architecture began with ARM7, frankly speaking. ARM1, ARM2, ARM3, ARM4, ARM5. This architecture, these versions of the ARM architecture were not so popular as it was expected. But the real popularity of ARM shooted up with ARM7. So ARM7, ARM9 compared to ARM8. Next, ARM11 also compared to ARM10. So ARM7, ARM9, ARM10, ARM11, and after that you have the ARM Cortex series. In the Cortex series, you have the A series and the R series and the M series, where A series stands for application oriented CPU architecture, and R series stands for real-time performance-oriented CPU architectures, and M series stands for microcontroller-based CPU architecture. So you have the ARM ARM, that means the ARMs A series, R series, and M series. So you can see in the name ARM, it's also you are having the series called as ARM. ARM architecture name is ARM, where ARM stands for Advanced RISC architecture, Advanced RISC microcontroller architecture, you can say that. Okay, or Advanced RISC machines, actually speaking. ARM stands for Advanced RISC machines. It is CPU architecture, preferably used in the microcontroller series. And we have the R series, M series, and the A series, where A stands for application, R stands for real time, and M stands for microcontroller series. So we are going to learn about the ARM architecture from where the popularity began, that is the ARM7 architecture. And whatever features that you learn about this architecture mostly will be carry forwarded to the next versions of the architecture. So what you are learning is now about ARM7. These features of ARM7 that you know are also applicable in ARM9, are also applicable in ARM11. They are also applicable in ARM Cortex. But as you move from ARM7 to ARM9, some extra more hardware characteristics or features or instruction set will be added. If you move on to ARM11 also, some hardware features, characteristics or instructions will be added. ARM Cortex also, characteristics, instructions and features will be added. But whatever you're learning in ARM7 core, most of the features are carry forwarded to the next versions of the CPU architecture. So let's begin our journey in the world of ARM embedded systems. So basically, you know what is an embedded system, so I'll not be wasting time in trying to define what is an embedded system and all that. All I'm just trying to discuss is about the ARM architecture. So the acronym ARM stands for Advanced Risk Machine. So this was an architecture which was actually conceived by a company called as Acorn Computers Limited. Okay, somewhere in the early 80s, and in a very short interval of time, when this architecture was designed by the ARM Limited, it became very popular, and it was, I mean, became popular in the sense it was very attractive architecture. It was a very uh, captivating architecture or sought after architecture. And somewhere in the early 90s, the first risk ARM architecture had been released. So though the architecture was introduced in the early 80s, the first risk architecture had been released. So okay, now is it audible? Is it audible now? Okay, right. So the ARM embedded, the ARM architecture, which became it became popular in the early 90s itself. That was the first commercial risk architecture in the 90s that was released. But the real hit of ARM, means the real popularity of ARM, began somewhere in the mid 90s, maybe 95, 96, or probably like that, with what we call the ARM7 architecture. So actually, when the ARM was released in the early 80s, it is said, as I had read somewhere in the what we call articles or something like that, when it was released somewhere in the early 80s, it did not become very popular by then. And there was a duration where the research on the ARM architecture had come to a standstill, because probably the company, the partnership, the people who were involved in the company, that means the partners involved in the company called as Acorn Computers Limited, had kind of disintegrated from they had separated from the company, and then the company got collapsed. Uh, that was by the name Acorn Computers Limited. And then there was a standstill for the ARM project or ARM research. But somewhere in the 90s itself, again, probably one of the partners of the Acon Computers Limited had again set up the company called as ARM Limited. He again set up the company called as ARM Limited, which stands for Advanced Risk Machines Limited. And after he had set up the company somewhere in the 90s, then probably it was the mid 90s where he had released the first commercially hit architecture, that is the ARM7 architecture. And from then onwards, there was no stopping for the growth and the popularity and the domination of ARM architecture. I repeat, from the mid 90s itself, 95, 96. Is it not audible? Is it audible? Hello? Somebody, some people are saying audible, some people are not saying, I mean, a couple of people are saying voice is low. So the people who are saying voice is low or it is not audible, maybe it is an issue with their phone or network probably, because if I'm audible for others and I'm not audible for particular people, probably it could be an issue with their phone or else the network. Am I clearly audible? Means, are you able to hear all my words clearly? Okay, so many few people are saying yes and audible. Those people who are saying low voice and not audible, I think it may be an issue with your area itself, your network or your cell phone. Please check it out. Okay, I'm muting and unmuting. Now is it okay? Am I audible? Am I audible? So I mean, for some people who is saying not audible, I think it is a problem with them only. V19HE6S19 maybe a problem. It's there on your mobile phone itself or your network. Please check it out. Okay. Right. So I'm proceeding. So the ARM architecture became very popular in the mid 90s with the ARM7 architecture, which became a commercially hit architecture. And from then onwards, there was no stopping regarding the growth and the popularity and the domination of the ARM architecture in the field of embedded systems. So what is ARM architecture? Is basically ARM refers to a family of processor cores. What is ARM? ARM stands for Advanced Risk Machine. It refers to a family of processor cores that have been developed and is being constantly enhanced through time to meet demanding needs of applications in the uh, global market of embedded systems. I repeat, ARM refers to a family of processor cores which have been developed and it is being constantly enhanced to meet demanding needs of applications in the world of embedded market. So the ARM core itself, which is not a single core, but it refers to a family of cores. So these cores are being developed by the company called as ARM Limited. And once these cores are being developed by the company called as ARM Limited, they may be developed in the form of a hardware, that means in the form of a silicon wafer. Okay, they may be developed in the form of a silicon wafer, which we call as the hardware die, or you can say like that. And then the ARM architecture may also be developed in the form of a software uh, code, a source code. So if it is developed in the form of a silicon wafer and sold out to various semiconductor companies such as Atmel, such as Philips, such as National Semiconductors, such as Motorola, such as Texas Instruments, etc. So the ARM core, which is manufactured by ARM Limited, it designed or manufactured by ARM Limited, may be available in the form of two ways. One is called as a source code, one is called as a hardware silicon wafer. So whatever format it is available, or whatever form it is available, it is sold out to various semiconductor companies. And these semiconductor companies, what they do is they integrate extra units around the core and package it as a microcontroller mostly, and sell it out with their brand name, such as Philips ARM7 based microcontrollers, or Philips ARM9 based microcontrollers, or Atmel ARM7 based microcontrollers, or Atmel ARM9 based microcontrollers, or Samsung ARM9 based microcontrollers, like that. Uh, National Instruments, you have Texas Instruments, okay, different companies, Snapdragon. So what the semiconductor companies do is they purchase the core from the ARM Limited, either in the form of a silicon wafer or in the form of a source code, and then they package extra units or hardware around that core and sell it out with their own brand name. This is a small story about ARM family of processor cores. Is it understood up till here so far? Please confirm. Whatever I have said, is it understood up till here so far? Please confirm so that I can move ahead. Anybody wants to ask any doubts on what I have discussed up till here? Yes, please. Anybody wants to ask any doubts regarding what I have discussed up till here? Is it all audible to them? Are you all, am I audible to you? Are you able to get my words? Please confirm any doubts till what I have discussed right now about the introduction of ARM architecture. Okay, so the ARM architecture, ARM stands for Advanced RISC Machine. So this Advanced RISC Machine architecture is available in two forms. One is called as the hardware form. The other one is called as the software form. Software means source code. So the source code of the ARM architecture is written in a language called as a HDL, hardware description language. To be more specific, it may be VHDL, okay, or it may be Verilog, or it may be System Verilog. So hardware description languages are used, of course, to design the core. This is called as the backend of VLSI designing, and sorry, front end of VLSI designing. Very sorry, it is called as the front end of VLSI designing, and the back end of VLSI designing is the hardware part going into the design of the chip. So at the front end of the VLSI, what is happening is the source code is designed using a description language, and once the source code is designed to a description language, this source file of the ARM architecture will be sold out to semiconductor companies, so that these semiconductor companies may enhance the source code of the ARM architecture by adding extra more features through programming. And once they are done with that, once they're done with that, what they do is they again give that source code to a EDA tool. EDA means electronic design automation tool, such as Cadence, or you have, I forgot the names, I'm not an expert in that, of course, VLSI. So you have Cadence tool is there, you have, I think, Multisim or something like that. So the electronic design automation tools are given the source code of the ARM architecture, and they will produce what we call circuit level file, and this circuit level file will be given to what we call other expertise of uh, what we call electronic design, and these people will try to design the ARM architecture core from hardware perspective. So the core may be available in the form of a hardware logic to the various semiconductor companies, or the core may be sold out to other semiconductor companies in the form of a software uh, source code, which may further be extended by that company as per their requirement. So these are the two forms of what we call ARM processor cores or processor architectures. So the popularity became popular somewhere in the mid 90s, and from then onwards there was no stopping about the ARM core, and it has dominated the world of embedded market by more than 80% of products being designed using ARM architecture. Predominantly, more than 80% of the products are definitely what we call the cell phones, of course, mobile phones. Most of the embedded products are more dominantly what we call the mobile phones, and most of the mobile phones are controlled using what we call the ARM architecture. Of course, in the world of embedded market, there are other CPU architectures also, but ARM architecture takes more what we call percentage. Is it understood, please? Up till here, any more doubts? Okay, so just look at just examples of the products which are using the ARM architecture. As you can see, you have digital cameras, and you have printers. You will have what we call, of course, cell phones, no doubtedly. You will be having what we call navigation systems, and you are having what we call routers. So there are lots of devices out there. PlayStations also. So many of the ARM many of the products have been designed using ARM architecture. So these are another few examples of what we call the ARM architecture. Okay, so now what you see here is an introduction about the RISC design philosophy. So the ARM architecture, which stands for ARM, Advanced RISC Machine, is a architecture which has been based on RISC architecture. So what is the RISC design philosophy? In trying to design an ARM architecture, design any RISC-based architecture, let us have a general idea. So RISC architecture, RISC stands for Reduced Instruction Set Architecture. So primarily when we talk about reduced instruction set, it implies that you have less number of instructions. Complex instruction set architecture, which is CISC, which means more number of instructions. Reduced instruction set architecture means less number of instructions. Though these less number of instructions are there, which are used for designing a CPU, these less number of instructions are very, very effective and very, very powerful, because they are designed to execute mostly in a single clock cycle. Okay, so their execution cycles will be a single cycle. But unlike CISC architecture, sometimes the execution cycle may be 1 cycle or 2 cycle or 3 cycles or 4 cycles, depending upon the CPU architecture. In RISC architectures, the execution cycle is constrained to be 1 clock cycle per execution. I'm talking about execution cycle, okay? I'm not talking about fetch and decode. So as far as execution cycle is concerned, it is reduced to 1 clock cycle, as compared to CISC architectures, where it may be 1 clock cycle for some architecture, for it may be 2 clock cycles or 3 or 4 clock cycles, like that, depends on the CPU architecture. But CISC architectures will have what we call more number of instructions, and their instructions will be complex in nature, and they will be taking multiple clock cycles to complete those complex operations. Here, the instructions are less in number, they are simple instructions, and all those instructions will be designed to be completed in a single clock cycle at operating at high speeds. Okay. So there are 4 major design rules whenever we're talking about the RISC architecture. One of the major design rules in RISC architecture is instructions. See, in CISC architecture, you have lots of instructions, but in RISC architecture, you have less number of instructions. So these less number of instructions are what we call mostly single cycled instructions. So maximum, the RISC architecture designer will keep in mind that the instructions will complete their execution mostly in single cycle. ideally speaking, but practically speaking, they expect, I mean, ideally speaking, they expect to design all their instructions to complete in a single cycle. That is ideally speaking, but practically that could not be realized, and a few percentage of instructions, maybe around if 90% of the instructions are taking single clock cycle for execution, maybe 10% of instructions will slightly take more than one clock cycle for execution. So they could not realize what we call uh, they could not realize the situation in which all instructions will complete in a single clock cycle. So mostly instructions are single cycle, except for a few instructions which could not be practically realized or designed to be single clock cycle. And these are mostly the branching instructions. Okay, these are mostly the branching instructions. Apart from branching instructions, there are also other types of instructions which will take more than one clock cycle for execution. So since the instructions are less in number in the RISC architecture, then what happens is the programming burden increases for the programmer. Since the programming burden increases for the programmer, that means if a person is designing a C compiler for a RISC architecture and the same person is trying to design a C compiler for a CISC architecture, can you people decide which person, I mean, if the person is designing a C compiler for CISC architecture and he is the person who is designing a C compiler for RISC architecture, for which case will he struggle more? Will he struggle more for designing a C compiler for CISC architecture more, or he'll struggle more for designing a C compiler for RISC architecture? Please, can you people comment using your thought process? I'm not talking about, okay, I mean, what do you mean by CISC? The person will suffer mostly for CISC or mostly for RISC in designing a C compiler. Some people have said CISC, some people are saying RISC. Okay, let me burst the bubble. So here it is, the RISC architecture. The person who is designing a C compiler for RISC architecture will have to struggle more in trying to design a C compiler for RISC architecture as compared to the person who is trying to design a C compiler for CISC architecture. Reason: the C compiler for CISC architecture can be easily designed in CISC. Why? Because CISC has a variety of instructions. It has a large set of instructions and it has varieties of instructions. So there may be some instructions which can be directly, I mean, which can be quickly interpreted by the C compiler because of the availability of that instructions in the CISC architecture. But since in RISC architecture, it's a reduced instruction set architecture, and availability of some kind of complex instructions may not be available in RISC architecture. So what happens is, using the available basic instructions of the RISC architecture, the compiler has to, the person who is designing the compiler has to what we call synthesize a complex operation of a CISC architecture through the basic available instructions of RISC architecture. Means, let me just give a simple example. It is not an exact example, but just to give an idea. Suppose, let us say CISC architecture is having multiplication instruction and division instruction, and a RISC architecture does not have multiplication and division instruction. Okay, it is not always the case. There are RISC architectures which will have support for multiplication and division instructions, and there are RISC architectures which do not have support for multiplication division also. So I've just taken one example here right now to explain the scenario. Let's assume that the RISC architecture is not having support for multiplication and division instructions. So if it is not having support for multiplication and division instructions, then what happens is the multiplication in RISC architecture should be realized through repeated addition, and the division in RISC architecture should be realized through repeated subtraction. That means generally any CPU architecture will have support for addition and subtraction because these are primary instructions of a CPU. So any CPU will be mostly having the primary instruction set which consists of addition, subtraction, but it may not have support for some kind of complex instructions. So let us assume that multiplication and division are instructions which are not available in RISC architecture. If it is not available in RISC architecture, then what is going to happen is we have to realize the multiplication and division using repeated addition. So repeated addition means we have to go for looping method as well as using add instructions several times through looping method to realize what we call addition. Similarly, division has to be realized through repeated subtraction. So you can see that by using the basic available instructions, okay, by using the basic available instructions inside a CPU architecture, we are able to realize a bit more complex instruction by using repeated addition or repeated subtraction, which is an iterative method or looping method to do that operation. So this is what we mean by synthesis of complicated instructions. Since RISC architecture does not have support for large instruction set, it has support for comparatively less instructions as compared to CISC. So if I want to realize an operation which is available in the CISC architecture but is not available in the RISC architecture, I have to use the basic available instruction in the RISC architecture to realize that complex instruction in CISC architecture using what we call synthesis of instructions. Using the synthesis of instructions. So this is also a major design rule which has to be kept in the mind, that instructions are mostly single cycled and very few instructions will be of more than one clock cycle, and it is the responsibility of the designer of the C compiler for the CPU to synthesize complicated instructions. And RISC architectures make use of this mechanism called as pipelining. CISC architectures may make use of pipelining, may not make use of pipelining, but RISC architectures make use of the concept or mechanism of pipelining. So what is pipelining? Pipelining in simple words means parallel operations are taking place, or inside a CPU, parallel activities are taking place in the same clock cycle. That means in one clock cycle, let us say fetch is taking place. In the same clock cycle, decode activity is taking place. In the same clock cycle, execution activity is taking place. In a non-pipelined CPU architecture, after fetch operation is completed, then only decode operation is completed. After decode operation is completed, then only fetch, decode, execute operation is completed. And after completing execute operation, again it will come back to fetch. So fetch, decode, execute. Fetch, decode, execute are occurring in the case of non-pipelined CPU architecture separately. First fetch, after fetch is complete, then only decode. After decode is complete, then only execute. So this is called as non-pipelined CPU architecture. Unlike that, in the case of pipelined CPU architecture, the scenario is fetch is taking place for the first instruction. The second instruction, as it is getting decoded, the first instruction as it is getting decoded, simultaneously the second instruction is fetched within the same clock cycle. When the second instruction is getting executed, simultaneously the second instruction will be getting decoded. Simultaneously, the third instruction will be getting fetched. So what happens is, in every clock cycle, more than one parallel activity is taking place. More than one concurrent activity is taking place. In every clock cycle, more than one parallel activity is taking place. More than one concurrent activity is taking place. So this gives rise to a better performance in the CPU architecture. Better throughput, better performance, and time taken to complete the application or instruction will be faster. So this is accomplished using the support of what we call fixed length instructions. So if ARM architectures have fixed length instructions, then it will be easier for the pipelining to transfer the instruction from one stage to another stage to another stage. So the pipelining stages are supposed to accommodate the instructions. So once the instruction comes from fetch state, then it should be given to the decode state. From decode state, it is given to execution stage. And if all the stages are having equal sized buffers, it becomes easier in order to execute the instructions in a very fast pace. Simultaneously, more than one instruction is being involved in some operation or the other. This is called as pipelining methodology. And if the instructions in ARM architecture are having fixed length instead of unequal lengths, then this pipelining will play a very significant role in executing programs or tasks or applications very, very fast. Yes, people, I have explained the first slide, which is talking about the four major design rules of risk architecture. And in the four major design rules of risk architecture, I have tried to explain the importance of the instructions related design rule. Is it understood? Please let me know, or you can ask your questions. Yes, people, is it understood? Do you have any questions on this slide, which I have tried to elaborate or explain? Hello, people, do you have any questions on this slide, which I have tried to explain?
Daddy.
Hello, any doubts? Once again, the last point. Okay, fixed length. Once again, the last point, that is pipelining. Pipelining is a mechanism used in CPU architectures. What is the mechanism is? Pipelining is a mechanism where parallel activities can be taking place simultaneously in the same clock cycle. Parallel activities can be taking place simultaneously in the same clock cycle. Means what? In a non-pipelined CPU architecture, what happens is after fetch stage is completed in, let us say, one clock cycle, decode state is probably taking place in the second clock cycle, execution stage is taking place in the probably the third clock cycle. So just assume that fetch takes one clock cycle, decode takes one clock cycle, and execute takes one clock cycle for one instruction. After that, again fetch takes one clock cycle, decode takes one clock cycle, execute takes another clock cycle for second instruction. Then for third instruction, fetch takes one clock cycle, decode takes one clock cycle, execute takes another clock cycles. That means 9 clock cycles have completed so far. In 9 clock cycles that has completed so far, what has happened? Only 3 instructions have completed their operations. This is what happens in a non-pipelined CPU architecture. In case of a pipelined CPU architecture, when the first instruction is fetched and it goes to the decode state, so decode first instruction is getting decoded in the second clock cycle. At the same time, in the second clock cycle, the second instruction is being fetched. And when the instruction goes to the execute state in the third clock cycle, at the same time, the second instruction, okay, the instruction in the second stage will come to what we call, sorry, once again, just hold on, please. My mouth is getting dried up. Okay, so when the first instruction comes into the fetch state and the first instruction goes into the decode state in the second clock cycle, simultaneously in the second clock cycle, a second instruction is being fetched. When the first instruction goes into the execution state in the third clock cycle. Simultaneously in the third clock cycle, the second instruction is being decoded and the third instruction is being fetched. That means in the third clock cycle, 3 parallel activities or 3 concurrent activities are taking place. First instruction is being executed and second instruction is being decoded and third instruction is being fetched. So what happens in third clock cycle, 3 parallel activities are taking place. In third clock cycle, 3 parallel activities are taking place. First instruction is being executed, second instruction is being decoded, third instruction is being fetched. So at the end of by the end of third clock cycle, 3 parallel activities are taking place. Whereas in the case of non-pipelined, only one instruction is getting executed in one clock cycle. Then the second instruction gets, the first instruction gets decoded in the second clock cycle, and the first instruction is getting executed in the third clock cycle. That means by the end of 3 clock cycles, only one instruction is getting effectively finished by the end of third clock cycle in a non-pipelined CPU architecture. Whereas in the case of a pipelined architecture, at the end of the third cycle, one instruction is getting executed, another instruction is getting decoded, another instruction is getting fetched. So that means the throughput of the CPU is getting increased. So if this throughput of the CPU is getting increased, it will have a good impact if the length of the instructions are of the same. If all the instructions are of the same size, then the throughput will be even, smoothly distributed. Okay, the number of instructions that can be executed will be smooth, whereas if the instruction size is of different lengths, then the throughput will be affected. So having fixed length instructions is really helpful in the case of pipelining. So RISC architecture designers would preferably design instructions to be of fixed length rather than of variable lengths like CISC architectures, where instructions may be of 1 byte size or 2 byte size or 3 byte or 4 bytes, 5 or 6 bytes like that. Here in RISC architecture, any instruction you take will be of the same size in terms of execution, in terms of sizes. Most of the instructions will take the same time except for a few. Okay, people, is it understood here so far regarding this first slide? Any more questions on the first slide here? Okay, moving on to the second slide. So just have a reading of this slide because it's already explained regarding pipelining. Okay, guys, second slide is understood. Same thing which I had discussed, that pipelining refers to parallel activities taking place within the same clock cycle, or it is also expressed as processing of instructions broken down into smaller units that can be executed in parallel by pipeline. So the primary advantage of pipelining is it increases or maximizes what we call the throughput of the CPU. Throughput means, throughput is defined as the number of instructions that can be executed per unit time is referred to as throughput. If more number of instructions that can be executed per unit time are increased, that means the throughput of the CPU is said to be increased. Next, look at the third, what we call a design philosophy. Now, CISC architectures are having a large instruction set, but when we compare an 8-bit CISC architecture with an 8-bit RISC architecture, or we compare a 16-bit CISC architecture with a 16-bit RISC architecture, or if we compare a 32-bit RISC architecture with a 32-bit CISC architecture, like that, the number of internal core registers present in the RISC architecture are usually more in number as compared to the number of core registers present in CISC architecture. So we say that the RISC architecture supports register intensive processing and CISC architecture supports memory intensive processing. Most of the instructions in CISC architecture will be using the operands as memory, whereas most of the instructions in RISC architecture and very rarely other instructions. So most of the instructions in RISC architecture will be making use of registers as their operands. So registers are the entities which the CPU architecture mostly acts upon to perform operations. So let it be addition, let it be subtraction, let it be multiplication or division, let it be incrementing or decrementing. So most of these arithmetic and logical operations are accomplished by using registers as their operands, but not memory as operands. Like in 8051, we have add accumulator comma address location, add what we call subtract accumulator comma address location, increment address location, decrement address location. Okay, we have instructions which are dealing with addresses or memory as operands, but RISC architecture does not encourage memory or address as operands. RISC architectures will encourage only registers as their operands rather than memory as their operands. So if registers are increased as their operands, use of registers only is increased as their operands, then what happens is the system becomes more faster because registers are more faster storage devices inside the CPU architecture as compared to memories. It is easier for the CPU architecture to read and write with respect to memory as compared to reading and writing with respect to memory, internal or external memory, ROM or RAM. It can read from registers more faster as compared to reading from RAM location or ROM location. Hence, because of the large set of registers which are preferably used for RISC architectures, okay, it helps the CPU to operate much more faster in contrast to CISC architectures. Is this understood, please? Throughput is a terminology which is used to define the number of instructions that can be executed per unit time. Throughput is a terminology which is used to express the number of instructions that can be executed per unit time. That is what we mean by throughput of a CPU. So throughput of a CPU can be divided into two types. You have instruction or execution throughput. We have instruction or execution throughput, and then we have data throughput. Instruction or execution throughput. Instruction or execution throughput implies that the number of instructions that can be executed per unit time is referred to as instruction or execution throughput. Whereas the number of data bits, that can be transmitted from a register to a memory location or from a memory location to a register in a single instructions, that will be deciding the data throughput. Only 8 bits can be transmitted from register to memory and vice versa in a single instruction as compared to 16-bit information being transmitted from register to memory, memory to register, like that in a single instruction, as compared to 32-bit instruction being transferred from register to memory, memory to register. So we say, in other words, that the data throughput increases. So data throughput means number of bits that can be transferred in an instruction in an architecture. If more number of data bits can be transmitted from source to destination and vice versa in an architecture, we say that it has a higher data throughput. But if more number of instructions that can be executed per unit time, we'll say it's having a higher CPU or execution throughput. Is the word throughput understood? V19H6H1. Okay. So have you understood the significance of risk architecture in terms of what we call registers, in terms of pipelining, and in terms of instructions? Everybody, have you people understood the significance of what we call registers or pipelining or instructions in risk architectures or in CPU architectures? Please, if you have any more questions, raise your doubts. Yes, please. Any questions? Please raise your doubts. Hello. Any doubts, please, regarding what I have discussed? Please come out and raise your doubts. Anything that, any word or any sentence that you have not understood, you can try to ask. I'll try to clarify. If you're not asking doubts, I will assume that you have understood whatever I have discussed. Okay, then nobody is asking doubts. So I'm assuming that people have understood what I have discussed so far. Okay. So the four major design rules, one is based on instructions. The next one is based on a concept called as pipelining. So pipelining must be there in a risk architecture. Pipelining may be there in a risk architecture, may not be there. But any risk architecture must support pipelining concept. Any risk architecture must support what we call single cycle instruction execution mostly. Okay, and any risk architecture must support a large set of registers. So an 8-bit risk architecture, 8-bit risk architecture, if we compare, 8-bit risk architecture will have more number of internal registers. Same like 16-bit risk architecture, same like 32-bit risk architectures, and so on. So the number of registers in the core will be more in the case of risk as compared to CISC. What are the reasons? I have already explained it. Moving on to the next slide. So risk architectures follow what we call a policy called as load store policy. So what is this load store policy? Is any instruction the CPU has to offer, any data the CPU has to operate upon. I repeat, load store architecture implies that any data the CPU has to operate upon Okay, somebody is asking what is pipelining. V19HE7M3 is asking what is pipelining. Pipelining refers to a mechanism used in CPU architecture whereby parallel activities are taking place concurrently in the same clock cycle. Pipelining refers to a mechanism in the CPU which is designed such that parallel activities are taking place simultaneously inside the CPU. Parallel activities are taking place simultaneously inside the CPU for the same clock cycle of time. That is called as pipelining. Is it understood? V19HE7M3. Now coming to the load store architecture. So load store architecture implies that if any risk architecture has to write any information, it has to operate on any data. It has to update a register or it has to operate on any data. Then risk architectures will support only the load store instructions to do that. That means whatever data that has to be operated upon, that data is available in a register. It must be brought, that data is available in, let us say, a memory location. It must be brought from a memory location into a register to be operated upon. So bringing data from a memory into a register is called as loading data into register. And once we operate on the register, the data, we have to update that operated value into what we call the memory once again, so that it will be available in the memory for future reference. This is called as store. So loading means getting data from memory into register. Storing means putting data in from what we call putting data from register back into the memory location. This is called as load and store policy. So because of the load and store policy being used in this architecture, many instructions have been eliminated, which are involving what we call many instructions which are involving the use of addresses or memory as operands have been eliminated, and instructions which are mostly dealing with registers have been included in the RISC architecture. So because of this load store instructions, what is the benefit is all the data which has to be operated upon must be brought from memory into register. Then it has to be operated in the register quickly and fastly, and it has to be placed back into the memory location once again. So this type of policy is called as load store policy, and this load store policy leads to what we call register intensive processing. So most of the processing is done with respect to registers. So the benefit of this register intensive processing is it maximizes the access of register banks in the ARM architecture. It minimizes the multiple access of memory. So if minimizes multiple access of memory, that means the performance automatically increases, because accessing memory is a slow process as compared to accessing a register of a CPU. Is the fourth point understood? Please comment on that. If not, if you have any doubts, please ask. I will try to clarify. Have you people understood the fourth point? Please comment. If not, or ask any doubt if you have any. Any doubts on the fourth point, please? Okay, the fourth point says load store architecture means in a RISC architecture, if a data has to be operated upon, it cannot be directly operated upon when it is available in the memory. The data to be operated upon as available in the memory must be brought into a register, which is called as load operation. Means loading information from memory into register to operate on the data present in the memory is called as load operation. After the load operation is completed, we operate on the data in the register. So loading information to be operated upon from memory into register to operate is called as loading. After the loading is completed, we do the operations in the register, and after the operations are done in the register, finally we can again update the data back into the memory location. This is called as load store architecture policy. Is it understood? Okay, somebody is asking a question, why in memory it is slow and in register it is fast? Because memory in terms of design itself, memory unit in terms of design is using a different technology, and register in terms of design is using a different technology. Register uses high-speed switching technology and memory uses less than high-speed switching technology as compared to a register. So the storage units are two different storage units. Their design type is also different. So the registers use more faster switching method technology. Memory uses less faster switching method. Hence, always registers are more faster than memory. But you never hear about a CPU which is having 1 GB of registers or 2 GB of registers like that. So the number of registers inside CPU architectures will be not very much as compared to the memory that can be connected to the CPU. V19HE7M3, is it understood? Anybody, any more questions, please? Anybody, any more questions regarding the 4 slides and whatever I've discussed in this 4 slides? No questions then? Okay. So we come to the end of the discussion of what we call the 4 major design rules in RISC architecture design. One is instructions have to be kept in mind in terms of design. Next is what we call registers. Next is the pipelining. Next is the load store architecture. These 4 major rules should be kept when designing a RISC architecture in mind. So the next slide is talking about the ARM7 architectural features, which we will be discussing, but not today. We'll continue tomorrow. So now it's almost 11:36. What we do is we'll have a 20 minutes break. Okay, 20 minutes break means I'm rounding up to 11:40, assuming. So from 11:40 till, let us say, 12. So 11:36 till 12 is your break. And after break, we resume and we continue from 12 o'clock with the I2C discussion. Okay, guys? At 12, we continue with the I2C discussion. So take a break and come back.